Hello, welcome back to Lesson 2 in our Unit 5 in our Data Structures and Algorithms course. We are studying minimum spanning trees and weighted graphs in this lesson. We're going to be breaking this lesson down into two parts. So our first part of this lesson will simply be dealing with minimum spanning trees of non-weighted graphs. So that's going to be our goal in this lesson, and then we'll look at weighted graphs in the next one. Okay? So a tree graph that when superimposed onto a graph connects all the vertices is called a spanning tree. So remember that a spanning tree, a tree graph cannot have a cycle. So you can see I've got a graph here below, and this definitely is not a tree because it's got cycles, like ACB is a cycle that goes in a loop. But if we want the minimum cost spanning tree, we want the smallest tree possible that connects all the edges. So let's see if we can't make one. There's probably lots of correct answers. And usually we show it with like dashed lines on top. See, we're superimposing it. So I'm gonna start with C as kind of my center hub. And we can go there. Now the question is, should I connect B and F? Well, if I did, I'd have a cycle. And if you have a cycle, you don't have a tree. So let's try this over here. And I could go like this as well. So there we go. I've got all my networks, all my little hubs connected in this network. So from any one of these places, I have a connected graph. I can reach from D to anywhere else by following one of the red lines because this is a spanning tree. Is it the minimum cost? Well, since this is an unweighted graph, I would say each edge is only a cost of 1. So 1, 2, 3, 4, 5, that totally would make sense. So I have a cost of 5 edges. And notice we have 6 vertices, and there will always be one less edge than there are vertices. Okay, so the good news is for this lesson, we already know how to do this. We have already learned how to find a minimum cost spanning tree because it is quite simply a depth first search. So we're beginning to understand when we use a breadth first and when we use a depth first. Breadth first searches can help you find the shortest distance to somewhere. It allows you to check all your neighbors first to find a solution. But here we see a depth first can be used to formulate a spanning tree, a minimum cost spanning tree on a graph with no edges. Excuse me, a graph with no weights. If we add weights to those edges, that's going to change it because then we have to look at, is this edge longer or shorter than that, and have to make some more decisions. All right, for this implementation, we will go ahead and use a stack because a stack is what makes you have a spanning tree. A depth first search uses a stack. I will be using the deck interface, and I'll implement it with a linked list, which is a doubly linked list. Okay, so let's go ahead and formulate. Let's take a look. Let's formulate a adjacency matrix for this graph. So we're going to solve this problem here. Now, we could probably do this by hand pretty easily, right? We could just kind of make our own little graph, but we're working on programming it. And we want to make it to where it could work for any adjacency matrix we give. And also keep in mind that while this graph is very simple, graphs can become incredibly complicated with thousands of different nodes that would make it very difficult to do by hand. So we want to automate this process. So what I'd like you to do is pause the video and go ahead and fill in the adjacency matrix that you would get from this graph. Okay, so hopefully you did that. I've got a little answer that I've created over here. And this is what I have for an answer. See if you agree with that. I actually kind of made this, just typed it up right quick, and I really didn't double check it myself. So we'll double check it together. A should go to E and C only. So A, B, C, D, E. Good. This row is for B. B should go to F and D. A, B, C, D, E, F. Okay. let's see here. This is row C. C goes to A and F and G. So A, B, C, D, E, F, G. Okay, this is for D. It should go to B, and it should go to F. Good. This is for row E. E goes just to A. All right, F should go to B, C, and D. B, C, D, and nothing else. And G goes only to C. Okay, so I like it. Let's go ahead and write our algorithm out, and let's do it. Okay, I've got here just a new BlueJ project called Minimum Spanning Tree. And I'm going to write this new class, and we'll call this class Graph. Kind of silly, but that makes sense. And I don't need any of this stuff, so I'll just Control A, select it all, and get rid of it. Okay, so I am going to be using java.util.deck. That is an interface that supports a stack, and I'll be using java.util.ArrayList, which is a doubly linked list which supports use as a stack or a queue. So that'll work well together. Okay. All right, let's start by making a our class here. Public graph, public class graph, and we're going to make an adjacency matrix. And my adjacency matrix could be true or false, or zeros or ones. So I'll just use 0 and 1. So I'll use int. Okay, and adj mapped. Oh, it doesn't like it. Oh, because go ahead and. All right, so then public graph. And we're going to allow us to just call the constructor with the adjacency matrix that we want. There we go. All right, so that's gonna set up the scenario, and now we're gonna write a method to find the minimum spanning tree. And there's lots of different ways we could do that. I think what would be nice is if we were to return a list of the minimum spanning trees. We could return a list. We could also return an array of them, since we know how big it will be. We know the minimum spanning tree must be equal in size to one less than the vertices. So why don't we go ahead and do that? We'll do an array. And I'm going to be calling them, they're going to be an array of edges. So I'll say edge. We'll have to define that class. And that would give minimum spanning tree, MST. We'll just call it that. All right. As you can see, we're going to need a nested class here. So I'll say private class edge. And they have two pieces of data that's important. Private int. I'll call this node A for starting node, and private int. You know what? Let's not call it A. Maybe let's call it start node. And I'll call this end node. Even though it's a non-directed graph, we can think of a start and an end. That'd be fine. Private edge. I'll take in an int. I'll just call it int A and B. So start node A, end node B. All right. So now our goal here is going to be to find this minimum spanning tree and be able to describe it using these edges. And I think it would be worthwhile to go ahead and make a public toString method. And I'll just return start node, and I'll do this indicating that it's the nodes that it's going between, and that'll cast those integer values as a string as well instead of adding them. All right, so there we go. Now on our edge method, we're going to be using our depth first search, but which means we'll be using a stack, but we're going to be using a stack of edges. So I'm going to say dec, because dec is the interface that implements that can be used to implement a stack of type edge. And linked list is the class that we'll use. And we can start at any node we want. We'll start at our initial node A. I'll say int current node. So I'm going to just make a current node, and I'll just start at 0. That seems like that would be a reasonable place to do. And we need to continue as long as there are different edges in our stack. And right now, though, the stack is empty. So I'm going to fill it first off with everything I can from node 0. So I'm going to do this in a couple different phases. So I'll say for int I equals 0, I less than adjmat.length. Or, technically adjmat bracket current dot length, but remember it's a square matrix, so it really doesn't matter. I plus plus. And I'm going to just look and see what all I can get to from my current starting node. So I'll just do this simple list here. If adjmat bracket current bracket I does not equal 0, since we're just using 0 or 1 for connected, then I can make a connection here. And we haven't visited anything yet, so I don't need to check on that. In fact, I haven't even made my visited Boolean thing. So I'm going to say stack dot push a new edge that is current to I. And that should get our stack started. Okay. All right, and we're going to go ahead and make our visited array now. So I'll say visited Boolean visited equals new Boolean array of size adjmat. And we have already visited current, so I'll say visited bracket current is equal to true. I need to say adjmat.length. All right. Boolean array visited. Okay, that looks better. All right, so now that we've got some stuff in our stack, if we didn't, that means it wasn't connected. So I'll say while not stack dot is empty, then we're going to pop from the stack. We'll say edge e equals stack dot pop. And when I pop off the stack, I want to consider that the second node, this end node, is where I'm at. So now I'm going to say current equals e dot end node. And then I can loop through like so. And I can say if adjmat bracket current bracket I does not equal 0, and I have not visited I, and I don't think there's really any fear of adding the same edge twice, so I'm not even going to worry about that. I'll just go, if I need it later, if I figure out, I can go back and add it. But we could check to make sure that we haven't already added a link from this edge to that, but I don't think that that's possible logically. We'll go ahead and say stack.push new edge And our new edge is going from current to I. Okay. So, where do we add to this edge array that we're going to return? Well, first of all, we need to have that edge matrix, edge array. So edge array, and this is going to be our tree. And we know that our tree has to be a number of edges, one less than the number of nodes. So if I take edgemat.length minus 1, that will be the number of edges that are needed in my tree. All right, so now we're ready to visit. So as soon as we pop an edge, first thing we're going to say is, well, we have visited where it leads to. Remember, we've already marked visited from where it started. So I'll say visited e.endNode. That's going to be true. And edge, we're going to be adding our edge. We'll say tree, and we've got to count. We've got to count the number of things that we've been adding. So tree count, since we start at 0, will be equal to the edge. And then I will increase my count for next time. All right, so that should be good. Now, the only thing about this is that it's going to keep trying to add more and more of these edges. So I'm going to stop. I'm going to add a condition in my while loop. I'm going to say and that our count is less than. We want to make sure that our count is less than the number of nodes in there, which we could just say we could just say, let's see here, tree.length, because that's what we're adding it to. That just keep me from going out of bounds. Okay. All right, and now I have a test method here that I'd like us to use. This is the matrix that we created earlier. I just create that integer matrix, and then I make a graph, and I'll call the MST method on that graph object, and then I just print out the edges. So let's give it a try and see what happens. So I run it's a static test, so you see it show up. All right, and that's what it gives me. Let's see if we can't plot these. Okay, so first thing I'm going to do is number these to make these a little bit easier for me. They are in alphabetical order. So 0, 1, 2, 3. And we could actually code it to where it printed out these letters fairly easily. 0, we could map to A and all that stuff. 4, let's see here. This would be 0, 1, 2, 3, 4. I guess that would be a 5 and a 6. Okay, let's see what they told me to do. So from 0 to 4, that's one of them. Then 0 to 2, 2 to 6. 2 to 5, 5 to 3, and 3 to 1. And so we have created our minimum spanning tree. We have no extra cycles, and we have a tree. And that's all there is to it. Okay, so with that, we will end the lesson.